Talking about spectral response, we have to take into account that one very important tool that helps us visualize the spectral response is a spectrum analyzer. And the spectrum analyzer uses an algorithm to present to us even complex signals as discrete frequencies. What that would entice is that presenting everything as single harmonics. Now, to explain that better, you just heard me in a lesson before in basic wave shapes, how I mentioned that a sine wave has only one harmonic. Now I'm going to demonstrate that by playing a sine wave. Now you see, it only has one harmonic coming out. One discrete frequency from a sine wave. Now if I play, let's say, a sawtooth on that same note, that is what I get. So I'm not getting only one harmonic, I'm getting multiples. And for a sawtooth, I'm getting all harmonics, odd and even ones. So if I play a lower note, you will see even more of that spectrum. Even lower. So you can see it has all of the harmonics, odds and evens. And what I mean by odds and evens is the multiples of that first harmonic that you saw for the sine wave. So that's a fundamental harmonic depicting the frequency that the sound is playing. Now all the additional ones are harmonics that the sound possesses next to the fundamental that we saw in the sine wave. So those are just multiples of the fundamental frequency. So when I say odds and evens, I mean the odd and even number of multiples of that harmonic, of that fundamental harmonic. So times 2 would be an even harmonic, times 4 would be an even harmonic of that frequency, and all the odd numbers like 3, 5, 7 would be the odd harmonics. Let's get back to the sine wave. Only the first one, sawtooth. All of them. Now to compare that to why odd and even, let me show you the square wave, which only has the odd harmonics. So compared to a sawtooth, the ones in the middle, in between of these, are missing. So let me switch from a sawtooth to a square, or from a square to a sawtooth, so you can see the difference. You see how a sawtooth just adds those even harmonics in there. Now a spectrum analyzer helps us visualize signals in a spectrum domain and shows us all of the discrete frequencies. So all of the discrete frequencies contained within that repetitive, we are presuming repetitive just like this one, repetitive signal. Now what this shows us is that actually a sawtooth can be made out of a lot of sine waves of different frequencies, and so can the square and the triangle. So let's see a difference between, let's say, a square and a triangle. So if you can't tell, they have all of the same harmonics. They have the same harmonic content. It's only the amplitude that differs for the square and triangle. So they have only odd harmonics, both of them, but those odd harmonics in the triangle, they progressively attenuate faster as the frequencies get higher on the actual content of the harmonics contained within the triangle wave shape. So let's go over that again. We have a sine wave with only one discrete frequency, so only one harmonic. Just like that. We have a sawtooth that has all the harmonics, odds and even. We have a triangle that has only the odd ones, but they attenuate faster as the content goes higher in frequency. And we have the square wave that doesn't attenuate as fast as the triangle. This shows you, of course, what I mentioned before, that all of these signals could be constructed using a vast number of sine waves. So any repetitive signal, just like this, any waveform can be created by adding up a large amount of sine waves of different frequencies, and of course in the right phase, and of course in the right amplitude. As you've noticed, the square and the triangle only differ by the amplitude of the harmonics contained within the signal. Now, let's see the only one signal left that we mentioned before that we didn't see so far, and that's the noise signal. You see, it's actually flat, so it covers all of the frequencies in the spectrum with the same amount of amplitude. That's white noise. And usually all of the spectrum analyzers are calibrated to this kind of measurement. So all of the spectrum analyzers are calibrated so that when you play white noise through them, it turns out flat, just like it was right now. So let's go into this. Why do we use a spectrum analyzer? Why do we need to see the signal? Well, some things are much easier to see than to, determine by ear. Something really precise as a frequency of something is much easier to determine by having an analyzer and reading it from an analyzer. So imagine I had a whole song and something was peaking out just like this. On an analyzer, it would be easy to spot that. Now let's see, what do I get when I actually add another oscillator to this? Let me just copy the one before. Okay, so let's say we add a sawtooth to this sine wave, and we're going to make those phases fixed to whatever setting we want, and we will talk about this also in detail. Don't worry about it. For now, I just want to show you the phase change between these two. Now, we talked about the phase, the first part of this waveforms lesson, and if I change the phase of this sawtooth while I'm playing both of these, we're going to see some harmonic shifts right there. So just look at the screen of this spectrum analyzer while I'm playing a note and moving the phase knob, let's say on this sawtooth. So you can see the shift in this lowest harmonic right there. So I can change that value by also moving the phase of this sine wave. Just pay attention to the lowest harmonic right here. Let me play a higher note so you can actually get that. So you see, in a position where these two are in phase like that, the sine wave is actually opposite to the first harmonic, because the sine wave has only one harmonic, only that one. Look at it. So that harmonic, the fundamental, because it only has the fundamental, and the fundamental of the sawtooth are actually in opposite phases, so they actually attenuate one another. Now, when I put them in a phase where they are in a complementary phases, they actually amplify each other. Like this, they are louder. See that? When I bring it back. So, aside of having the amplitude matter, let's say I just lower the amplitude of this sine wave. Aside of that amplitude and the phase setting, I can also change the frequency of a certain oscillator compared to the other, like this. Those three values that we talked about already are the values that are the most essential for the most basic of oscillators. So frequency, amplitude, and phase. All of those influence how they mix with other oscillators in the synthesizer, and we get different sounds. Now let's try the same example on a bass sound. I'm going to try to make a bass sound here quickly, and don't worry about not knowing anything about all of these, about the filters and such. We will talk about this in lessons to come. This is sound design. For now, I just want to depict for you the importance of the spectrum analyzer. So on this bass sound, if I change the phase of this sine wave, as you've seen before, now it has less sub and maybe more bass, so it's kind of different, and it always is. So if I use, let's say, a square with this sawtooth, you see, they are both retaining the same frequency, so the same pitch. They are retaining the same level, but as I change the phase, they actually change a lot in the mix. And I can slowly change the frequency of one of them. So those would be the most essential of controls on oscillators. And you can see those depicted on a spectrum analyzer. Now, all this talk about the spectrum analyzer, why is it so important to actually see the music? Well, it's not important, but it's a big help. Imagine having a second sense for something. This is what you're getting right here. So you have your ears, which are the most important tool you have in audio engineering, music production, and you have that visual helper that helps you with some of the things that you might not identify so precisely as the spectrum analyzer will. Well, I see myself as a pragmatic person, and any kind of help, well, I'll gladly take it. This has proved to be a big help to me for years already. So start getting used to looking at visual helpers. And this spectrum analyzer is not the only visual help that we have for analyzing sound. We also have peak meters, volume meters that we already talked about in the digital audio workstation course. So we have the peak and RMS meters. We have the correlation meter that we did not talk about yet. And this analyzer particularly has that one too. The correlation meter actually shows us the correlation between two phases of the left and right. Okay, let's say I wanted to show you how this correlation meter works. I'm going to turn off the filter, bring these both to sine waves. They have the same frequency. They have the same panning. I'm going to turn one all the way to the left, or to the right, sorry, and one all the way to the left. Now they have the same amplitude. What I'm going to do is I'm going to change the phase of one of these. Now, when they are in the same phase, they're going to show the value of 1. But when they get to completely opposite phase, they're going to show the value of -1, meaning that they are completely inverted from one another on the left and right speakers. So this is what it shows us, how the left channel is connected to the right phase-wise. So in the same phase, 1. Opposite phase, -1. You hear the same sound. The level on the left and right are the same, but they are in completely opposite phases. Meaning that if I was to make that mono and actually glue those two channels into one, I would get no signal. You see that? You can see it, but you can't hear it. Because now, after this span, when I do that mono, it just doesn't exist anymore. So I'm going to move the span after this mono out, and you're going to see that nothing's going to appear there. As you can see, it's playing, the synth is playing, we have the signal on our oscilloscope, but we don't have any sound coming out. Now, this is what analyzers can help you with. The spectral, balance, stereo correlation between the left and the right channel, and the level meters. All of these help us design sound, produce music way better. And we are going to talk much more about the spectrum analyzer and all of its benefits in our mixing and mastering course. One thing I could mention for the end of this lesson is that you could always use the analyzer provided by Ableton. It's this one, and I just prefer Span, but you could always use the analyzer called Spectrum, and you can find that in the audio effects of Ableton. So you can find that spectrum right there, and you can spread it out to cover more of the grounds. And I could play you a note, let's say something like a sawtooth. So you can see you always have that analyzer coming from Ableton, and it also has a lot of options that you can set side of it like that. So this analyzer is also versatile. You can use that one in case you don't like the span from Xango. I really do, but it's your choice.